We got a classic proof today, and it is that if a function defined on the domain a to b to r is monotone, then it is Riemann integrable. There's a very classic proof. It's also very simple. First of all, what does it mean that a function is monotone? Well, a monotone function means that it is either only increasing or only decreasing. I mean, so only increasing or only decreasing. It can be it can be increasing and decreasing. If it's strictly monotone, then it has to be strictly increasing. But if it's just monotone, it can be increasing, then it can be 0 for a while, then increasing again, but it can never be decreasing, And then the same thing for decreasing strictly monotone function. So all we need to have it, all we want is that the function is monotone, and then it is Riemann integrable. And for a function to be Riemann integrable, that just means that for every epsilon greater than 0, we choose a partition. We choose a partition, so we have a function. We have a function, and then we split, on our interval a to b, and then we split this function into intervals, so into partitions. So let's say I split it into here, 1, 2, 3, 4, 5 into a partition of 5. So this is x0, x1, x2, x3, x4, and this is xn, x5. So this is a partition of a function, and then for each partition I have a lower sum and an upper sum. So the lower sum is just the sum of the rectangles where the function has its minimum value, so it'll be the sum of these rectangles, and then the upper sum is just the sum of the rectangles where the function takes its maximum. So it's going to be these slightly bigger rectangles, and it's going to be the sum of these bigger rectangles. Basically, I want, for every epsilon greater than 0, I want to find a partition such that the upper sum, so I can just denote it like I don't know, I can just denote it like the upper sum of our function and our partition, let's say pk, minus the lower sum, this is a terrible L, minus the lower sum of our function with this partition. This difference is less than epsilon, which just means that the upper and the lower partition get infinitely close to each other. So usually the partition has to be very small. I have to choose a very small partition, and the upper and the lower sum are basically the same thing. That means that a function is Riemann integrable. And notice, we don't assume continuity. So a function can be integrable. We know that a function can only be differentiable if it's continuous. But for integration, it's a bit less strict, even though integration is the inverse of, of differentiation. But we can have a function. We can have a function like this, then it's undefined here, then it has a jump over here, then it goes like this, and then it's undefined here, and then it goes like this. Like this function, it has jumps, but it is still integrable. It's not continuous. It has jump discontinuities, but it is still defined everywhere on its interval. At this point, it just doesn't equal this value, but it equals this value. So it's still defined on every interval, on every single value, but it doesn't have to be continuous. That's kind of a cool thing we're going to see in the proof. We don't actually need continuity for Riemann integrability. So what we're going to do is we're going to suppose f is increasing. So suppose f increasing. And now we're going to fix an epsilon greater than 0. This can be any epsilon greater than 0. Now we're going to choose a partition. We're going to choose a partition, Pn. I always make the P different. Pn of our interval AB, which we're interested in. And that partition, well, this is just going to be, again, okay, I can start with a little drawing. So we're going to have our function here. We're going to make it nice and big, let's say like this. And then again, I'm looking at the interval from A to B. This is the interval I'm interested in. And then I make a partition. So the partition, all of these partitions will have the same size. I'm going to have n of them. But the length of the interval is b minus a. B minus a is the length of the interval. And then I divide it by n. So if I want 10 partitions, I divide this by 10. And I get delta xn. So the size of each partition, this is delta x. The size of all these partitions will be exactly the same. And if the size of each partition will just be, this length, b minus a, over n. So over how many partitions I want. So this will be my partition of AB. This will be delta xn. And all of these will be exactly the same size. So, now I basically created intervals. I created n intervals. And, an interval is just defined from xn minus 1 to xn. This is, this will be the interval I1. And this, I can define a as x0, and then this can be x1. So this is I1, then this over here will be I2. So I2 will be, from x1 to x2, and so on up to in. And now, on every single interval, because f is increasing, I can say something special. Again, we can see our function f is increasing. So if I focus on this interval over here, I'm trying to find the maximum and the minimum of the function. So I can define ln. Let me go down a little bit. I can define ln. Let's say I'm gonna do this for every interval in. I can define a minimum and a maximum, or an infimum and a supremum on each interval. So the ln, the lower bound, the smallest value of the function, well, that would just be xn minus 1 in this interval. Because again, this is our interval in. In goes from xn minus 1 to xn. So the smallest value in in will be the first value of the interval, because again, the function is increasing. So, in each interval, the smallest value has to be the first value. And then the biggest value, well, the biggest value has to be xn. The biggest value has to be the biggest value in the interval. And then for the next interval, xn will be, again, the smallest value. They share this middle value. And then, xn plus 1 will be the biggest value. So in every interval in, the smallest value, or the lower bound, is fxn minus 1, and the upper value, or the supremum of the function, un, will be f of xn. Again, this makes very much sense. For this interval over here, this is the smallest, this is the biggest value, because f is increasing. I mean, because it's monotone. We can only say this because it is monotone. So now, what happens if I try to take upper and lower sums? Because the whole idea of Riemann integrability is you take upper and lower sums, and then you see, if you can make them equal for a certain partition. Well, I can first of all start with the lower sum of f and my partition Pn, and I can say that that would just be the sum from n equals 1 to capital N of f xn minus 1 times delta xn. This will be the sum of the lower bounds, because again, this fxn minus 1, this will just be the first value of each interval. So this sum, it starts with the first interval, so I can start drawing this. The sum starts with the first interval over here. It finds, it takes the first value of the interval, and then it takes, this value of the function times delta xn. Again, delta xn is just the size of the interval, so it computes this rectangle over here, and then it goes to the interval I2, and again, it chooses the first value, which is, again, the lowest value of the function, times delta xn, which is just, the same size always. So then it computes this area, and then for the next interval, it computes this area, and then, for the last interval, it computes this area. So that will be our lower bound sum. And now again, the same thing I can say for the upper bound sum. So the how do I draw this? I always forget how to draw a fancy U. So I don't know. For the upper bound sum of f and our partition, this is the exact same partition. They have to have the same partition. I'm gonna move this down a little bit. The upper bound sum will just be, again, our function. Our sum from n equals 1 to n of f of xn times delta xn. And again, this will just mean that for each interval, I'm taking the final value of the interval. I'm taking un, I'm taking the upper bound of the function. Now, again, for the first interval, that will be the final part of the interval. So we're going to sum up, this rectangle over here. It's going to be everything. It's going to be this extra area and this green one over here. But maybe I don't want to make it too congested. Maybe I'll just draw like 3 lines. I'm summing up this area, and then for the second interval, I'm summing up this area, and then oh my goodness, this looks terrible. And then for the second interval, I'm summing up this area again. For the third interval, I'm summing up the final value of the interval. I have this rectangle again. This is f of xn, and then this is delta xn, is just the constant. So I'm summing up this rectangle, and then for the final one again, I am doing the exact same thing. And now, if I subtract them. Again, here, just on the function, I can also label this on the function. This will be f of b, and this will be f of a. This is going to become cool in a second. That's why I'm doing it. But basically, if I now subtract the lower bound and the upper bound, the upper bound is always bigger than the lower bound. That has to be true. So I'll subtract the upper bound minus the lower bound of f and our partition. And now notice also delta xn. This has, for every single sum, this has a constant value. Delta xn will always be a constant, and it will just be b minus a over n. So again, I could just take this out. I will sum up. I will. This is just the same thing as b minus a over n, and I will sum it n times. I'll multiply this by the first value, by the second one, by the third one. So I'll just multiply all of these things by b minus a over n. So I can just take b minus a over n outside, because again, it's not affected by our sum. This is a constant, so I can just take them outside of the sum. So basically here I can just factor out b minus a over n, because this is just a constant. And then what I'm gonna be left with is this sum over here minus this sum over here. Now what is this going to equal? Well, that is just going to equal. You'll see what we're gonna get is a telescopic sum. Actually, I can just try to do this over here real quick. So from n equals 1 to n of f of xn minus the sum from n equals 1 to capital N of f of x n minus 1. How is this going to look like? Well, if I just expand this sum over here, this will be f of x1 plus plus f of x2 plus f of x3 plus so on up to f of xn. And then this over here, if I just expand it, these will all be negative because of the minus in front of them. So then, this I'll just add with, the first term will be f of x0, again, because it's, n minus 1, when n equals 1, n minus 1 equals 0, minus f of x1 minus f of x2, and so forth up to minus f of xn minus 1. Because, again, when n is capital N, that would just be, n minus 1. So basically, I get this over here, and you're going to notice that f of x1 minus f of x1, f of x2 minus f of x2, these all cancel. The only thing that remains is the first term and the last term. And again, we said that the first term, x0 is the same thing as a, and xn is the same thing as b. So what we're going to be left with is just f of b minus f of a. So if I go back to this over here, if I want to express this, this will be b minus a over n times f of b minus f of a. This is what this difference will equal. And again, we can get a geometric picture of this because the difference in the lower bound and the upper bound sums, as we have noticed, the difference is just these areas over here. It is these, because we have the lower bound rectangle, the upper bound rectangle. So the difference will just be these little columns over here. And again, we can stack these little columns on top of each other. So, if we imagine bringing this column, I'm going to use a different color. Maybe I'm going to use a blue. Let's just say I bring this column over here and draw it like this. And this column, I bring it over here. So I just draw it like this. And this final column, I bring it over here and just draw it like this. We see that we just get this column. And what is the width? So this area just adding all these columns, all these differences together, that will be the difference in our sums. And we can see that this is just a column. And again, what is its base? Its base is delta xn, and delta xn is just, its base will be b minus a over n, because that is just, that is just delta xn. That is just the width of each interval, of each rectangle. And then the height of this rectangle is f of b minus f of a. That is its height. So this is base, this is base times the height, which is just f of b minus f of a. This is, this is the difference between the upper bound and the lower bound sum. And again, this is, base times the height. And we can see, that this is exactly what we got over here. We got b minus a, we got b minus a over n times f of b minus f of a. So this is just, a visual intuition of this rectangle. And now we want this to be less than epsilon for a Riemann integrability. Again, we want to find a partition. This function, is Riemann integrable if for every epsilon greater than 0, there exists a partition such that the upper bound minus the lower bound sum is less than epsilon. And now we choose this partition, can be however small we want. This n can be whatever we want it to be. So we can see that if we want this to be less than epsilon, if we multiply n on the other side and do some rearrangements, we get that n has to be greater than b minus a. I can actually just draw this. So I multiply n on the other side, and I get that n, let me do this a bit nicer. I get that n has to be greater than b minus a times f of b minus f of a over epsilon. Now again, epsilon, we choose any epsilon greater than 0. So epsilon can be very small. Epsilon can be 0.00001. So this number will be very big, But again, these are constants. B minus a, this is just the interval we're looking at, and f of b minus f of a, these are also constants. So, the smaller the epsilon, the bigger this number will be. But again, n is just any natural number. N is just any natural number. And, natural numbers can go up to infinity. So no matter how big this number is, we can always choose, we can always choose a natural number n such that, I want to draw the natural number symbol, natural number n such that, I'm just going to give up on this, it's bigger than this number over here. That is a property of the natural numbers. Whatever number you have, you can always find a natural number that is bigger than that number. So nothing, for any epsilon greater than 0, no matter how small epsilon is, we can always choose a partition. This partition will be b minus a over n. This will be our partition. We can choose an n so big, depending on the epsilon, we can choose an n so big that these partitions will be very, very, very small. And what's going to happen, the size of this rectangle will be the same big. The rectangle will be the same tall, but the delta xn, the little intervals will get so small that this rectangle will basically become infinitely thin. You know, at infinity, you know, this rectangle will be so thin that, you know, the base will basically be 0. So it's gonna be 0 times height, and that's just gonna be equal to 0. You know, that kind of shows you that the upper sum and the lower sum will have to be equal at infinity. But again, we don't specify that they have to be equal. We just specify that the upper sum minus the lower sum have to be less than epsilon for any epsilon greater than 0. This we can always find a partition such that this is true. So that is the end of the proof. I think it's a pretty clean proof. You know, it's pretty easy. And now we can see we never in this proof that we need continuity. We can have a function which looks like this. So not defined here, defined here, not defined here, defined here, and this function is integrable on its interval a to b. There's nothing stopping us from saying that this function is integrable. Is a Riemann integrable. So yeah, that is the end of the proof. And yeah, that is it. Thank you for watching.